So this lesson on triangles is we're going to continue our special segments. We're going to talk about angle bisectors, perpendicular bisectors, and altitudes. So just a quick reminder, an angle bisector is a line array or a segment that cuts an angle into two equal pieces. A perpendicular bisector is a line array or a segment that cuts through another segment, does two things. It bisects it, so it cuts it in half, and it does it at a right angle. Perpendicular means lines that intersect at right angles. And then we have an altitude. We'll talk about that in just a second, but that we wanted to go back to previous units and remind you of some vocabulary. So if I take the angle bisector of each of these acute, right, and obtuse triangles, so just kind of eyeball it. I'm going to bisect this angle. And then I'm going to bisect this angle, Okay, so remember what I've done is I've cut these in half. Unlike the median, it does extend from the vertex, but all it does is bisect the angle. The median went from the vertex to the midpoint of the opposite side. The angle bisector doesn't care where it hits the other side as long as it bisects the angle that it leaves from. So if I eyeball this one, this right angle right here, I'm going to eyeball it and kind of bisect that angle, trying to get there a 45-degree angle. We're going to bisect this one. Oh, that's bad. Cut it in half, and then we're going to bisect this angle. Pretty close. Okay, I have bisected these, so I'm just marking that my pieces are congruent. That's my right triangle. And then I'm going to do the same. Again, remember that you'll see it here, how an angle bisector is different from a median because it doesn't go through the midpoint of the opposite side. We're just going to cut the angle in half. Oh, that one didn't go very well. So we come out here, bisect that angle, and then start here at this angle, and I'm going to cut it in half. Now, similar to the median, though, what you notice is that all of these lines, these angle bisectors, they have a point of concurrency. Remember, that point of concurrency is where the points intersect, where all the lines intersect. They all intersect right here inside the triangle. The point of concurrency is called the incenter. Now, what's cool about the incenter is the incenter is the point that is inside the circle, that is the center of this circle that would fit inside, that would touch all the sides. Now, again, they're not drawn exactly to scale, right? And so, but what this does is it gives us the center of the circle that I can draw inside. Okay, so the incenter gives us that circle that's on the inside. That's just a cool fact, but it is something that happens when you bisect the angles. You can find the center. Maybe you want to design a flag that is triangular in shape, but you want to fit a circle in it, and you want the circle to touch all three sides of the triangle. Then this is what you could find. You could find all the angle bisectors. That would give you the center of the circle. The angle bisectors always contain the vertex, because by nature they leave from the vertex and then they bisect the angle. Okay, and then we've got a perpendicular bisector. So perpendicular bisectors, they do not originate from the vertex. Okay, they don't originate from the vertex. So what you want to do is you want to look at your side, and then you want to kind of cut it in half. So we're going to find our midpoint. There's our midpoint. And then I'm going to draw a line in that's a right angle. Okay, so there's my perpendicular bisector. I bisected that side. Now let's bisect this side. So I'll find the midpoint, and I'll just kind of eyeball it, 90-degree angle. And then we'll do the same with this last side. We'll find our midpoint right here, and then we'll eyeball it, and we'll draw a line that extends through the midpoint. So the median goes from the vertex to the midpoint. The perpendicular bisector just goes through the midpoint, but it does it at a right angle. Okay, so if we do the same thing here, if I find the midpoint of that side and draw a line that's perpendicular, so that it'll cut it. I'm just eyeballing that perpendicular. Find the midpoint, draw a line that's perpendicular. I didn't draw this one long enough. And then find the midpoint and draw a line that's perpendicular. Notice that on an acute triangle, it meets all that point of concurrency is inside. On a right triangle, that point of concurrency is actually on the triangle. In fact, it's on the hypotenuse. Okay, on an acute, it's inside. And let's see what happens with obtuse, since these have been different. So we'll find the midpoint and we'll draw that perpendicular. Find the midpoint and draw the perpendicular. And then find the midpoint and draw the perpendicular. Okay, perpendicular, perpendicular, perpendicular. Notice that all these perpendicular bisectors intersect. They have their point of concurrency outside. Okay, so the perpendicular bisector does not include, it never includes the vertex. Okay, and its point of concurrency, that point where all three perpendicular bisectors meet, is called the circumcenter. Circumcenter. Circumference, remember circumference means around. So circum means around. So what we just found is we found the center of the circle that will let me draw a circle around the triangle so that all the points of the triangle are on the circle. It's kind of harder to draw this one because it'll be kind of big this way. But that's what it allows me to do. It allows me to draw, it's the center of the circle that goes around, like circumference, that goes around the triangle and makes it so that all three vertices of the triangle are on that circle. This is pretty cool. Okay, then lastly we have the altitude. The altitude, think about an altitude like a plane flies at an altitude. An altitude is a height. So what we're asking is then, how tall is the triangle? So if you imagine these triangles are like a piece of plywood, and depending on how I turn it, especially like that obtuse triangle, if I turn it and put the board so that this piece is on the ground, obviously it's not going to be a very tall triangle. So the altitude changes as you rotate this triangle around. So your altitude extends from the vertex, okay, perpendicular to the opposite side. So that's what's important. When you're measuring your height, you're told to stand up straight, or when you measure the height to a plane, the altitude to a plane, it's like it's dropping straight down. So imagine that you took a string with a heavy weight on the end and you hung it from this point. It's going to hang straight down like this, and it's going to hit at a right angle. Then imagine rotating this triangle. In fact, rotate your paper around so that you can see it. You're going to go from that point. Imagine hanging that heavy weight, and it's going to hit here. Now, it doesn't care where it hits the opposite side, okay? It's just going to hit somewhere, okay? So then we've got our altitude, and we've got it right here. So perpendicular. It doesn't hit the midpoint. The median hits the midpoint. The perpendicular bisector goes through perpendicular, but not from the vertex. The altitude goes from the vertex perpendicular. Okay, it kind of combines them all. So if we imagine this with this right triangle, if I hang a string with a heavy weight from that point, it's going to hang right straight down to there. If I rotate this around and set it on another end, imagine it's in plywood, right? And then hang that string down, it's going to hang down and it's going to hit that side. And then if I take it and I hang it from here, turn it so that this side is sitting on, the hypotenuse is sitting on the ground, then it's going to hang down and it's going to be perpendicular. Well, all three of those blue lines, right? This line, let me do them in a different color. This line, and this line, those were all my altitudes. They intersect right here. They intersect at the corner or the vertex where the right angle is on that right triangle. Okay, again, notice that in this case, in the altitudes meet inside. For the acute triangle, it meets on for the right triangle. Let's see what it does with this obtuse triangle. If I were to set this, a piece of plywood like that, if I were to set that piece, that blue line right there on the ground and then hang a piece of string with a heavy weight, the weight's going to hang down like this, so it actually hangs perpendicular to an extension of that side. Okay, so let me make it keep going. Okay, and then we need to do the same thing from another vertex. So imagine rotating it around now and setting it on that side. Then we're going to extend from the vertex perpendicular to that side. It's going to go right there. Imagine that it's extending backwards. And then if we rotate it and we set it on this side, we're going to hang a string from this corner and it's going to hang down. And it's going to be perpendicular to an extension. So it doesn't always go through the side. Okay, now look at where that is. Again, it's outside. Okay, it does extend. It does come from the vertex. So that's always, it extends from the vertex. Then when you have your circumcenter, their circumcenter was where your perpendicular bisectors met. Your end-center is where your angle bisectors meet. And the altitudes meet at a place called the orthocenter. Now I've looked and looked and I have not been able to find a simple application of where the benefit of the orthocenter. I'm sure there is one. I have just not been able to find it. So what happens when the triangle is isosceles? And what happens when the special segment starts at the vertex angle? So if we have an isosceles triangle like this, okay, where these two sides are the same, here is my vertex angle. So the question is, what happens to the angle bisector? Well, the angle bisector is going to come down, and I'm going to draw that angle bisector in. Well, when those two sides are the same, here's what happens. When I do the angle bisector, it's going to bisect the base. It goes through and it bisects the base. So that angle bisector does that. It also, the angle bisector is also going to be, so the angle bisector bisects the base. Well, we know that the median already bisects the base, so then the median goes from the vertex to the midpoint of the opposite side, which means the angle bisector and the median are the same thing. And the altitude goes down also, so the altitude, so here's what happens. The altitude and the median and the angle bisector, bisector, can't spell, are all the same. They all become the same when it extends from the vertex to the opposite side. The angle bisector, the altitude, and the median from the vertex angle of an isosceles triangle all do the same thing. They are all the same line. Now, if it's an equilateral triangle, then they're all the same from all three vertices. Okay, all the segments are the same segment. So the angle bisector is the median, which means it goes through the midpoint. It's perpendicular bisector, so it also bisects it at a right angle. And so it's the same segment from all three vertices. Where the isosceles triangle, they're all the same only from the vertex angle, not from the other two. Because if we drew them in from all of them, this is isosceles. If we drew them in from all of them, say for instance the median, it would look like this, and then it would look like that. But that that side is not this median right here is not the same as the perpendicular, right? So, and it's not the perpendicular bisectors. So you can see they're only the same when they come from the vertex angle. So let's look at some problems that have to do with this. Find the slope of the triangle's altitude through point A. So remember, an altitude extends from the vertex perpendicular to the opposite side. The opposite side is BC, okay? I want slope and I want altitude. Remember, altitudes are perpendicular. Perpendicular slopes are opposite reciprocals. So what you want to do is find the slope from B to C. Well, if you count all the way, just go from end to end, and then we can do little pieces later or reduce it later. So I go from 7 to 2. So that is 9. So I go 9 down. And I go from -4 to 3, so that is 7. So I go -9 and over 7. So I went -9 and I went over 7. And I just want to know the slope, so it can't be reduced. 9 over 7 can't be reduced. So the perpendicular, the altitude would extend and be perpendicular to BC, and it would have a slope. So the slope would be the opposite reciprocal. So opposite of negative would be positive, and reciprocal of 9/7 would be 7/9. So the slope of the altitude would be 7/9. It would look like this. I could go down 1, 2, 3, 4, 5, 6, 7 over 1, 2, 3, 4, 5, 6, 7, 8, 9. It would go through that point right there. And so if I actually wanted to draw in the altitude, I could, and I know that that will be a right angle. Okay, number 2, JH is an altitude. As soon as you see that word, you need to be thinking what that means. That means vertex to opposite side, and it is perpendicular. That's the important part. It's perpendicular. So HJ or JH is perpendicular. So that's a 90-degree angle. That's important. I want GJ. Well, GJ is a segment. There is no relationship between GJ and that angle at GJH. But what I do know is that right angles are 90 degrees. I have no relationship between GJ and JK, so I can't set that up. So here's what I do know. I know that because it's an altitude, it's 90 degrees. That means that 3x plus 3 is equal to 90. Okay, so I'm going to plug it in. 3x is equal to 87. We're going to substitute or subtract 3 from both sides. And 87 divided by 3 is 29. So we get that x is 29. I asked for GJ. GJ is x plus 8. So that would be 29 plus 8, which is 37. So GJ is 37. All because the altitude was 90 degrees. Okay, so find the orthocenter. Orthocenter means altitudes. Okay, so A is at 2, 0, and B is at 2, 4, and C is at 6, 0. So the good thing is that we have a right triangle here, and if you look back at your notes, with right triangles, it makes it really easy where to do. So imagine that you're starting at the vertex of B, and you're holding a string down. It's going to drop down right here, and it's going to land at A. If you rotate it and hold your string at C and drop it down, it's going to land at A. Well, since 2 of them landed at A, guess where the third one is going to land? It's also going to land at A. And remember, go back up here, altitudes. Here's my altitude right here, right? So it is right there at the right angle. So since this is a right triangle, then I know that my orthocenter is going to be at 2, 0, at the intersection of the legs of that right triangle. So on number 4, AD is a perpendicular bisector. 2 things, perpendicular, that's what that means, perpendicular bisector of BC. Okay, so a couple of things happening here. Notice that the perpendicular bisector actually happens to pass through the vertex. okay? It's actually happening to pass through the vertex. Because it's passing through that vertex, that's the vertex, then that means this is a vertex angle, which means that this triangle is isosceles. That means that these two sides are also congruent. So I can find the values of x and y by setting those pieces equal. So 3x minus 5 is equal to x plus 5. Subtract x from both sides, add 5 to both sides, and then divide by 2. You get that x is 5. Then you can do the same thing with y. Now that I know this is an isosceles triangle, 9y minus 13 is equal to 2y plus 15. Subtract 2y, add 13, divide by 7, and you get that y is 4. So I found my values of x and y because it was a perpendicular bisector. So this fact right here, the fact that that passes through the vertex, because normally the perpendicular bisector does not pass through the vertex. It doesn't, that's not how it originally was created. It just happens to pass through that vertex, which makes this into an isosceles triangle. This last one, segment MB, is an angle bisector. As soon as you read that, draw that in. It's an angle bisector. JMB, so JMB is this angle right here, is 3x minus 15. And KMB, which is this angle right here from K, if you trace from K to M to B, it's going to be that rotation in between. It's 5x minus 39. And angle K, which is this angle right here, is 5x plus 8. Find the measure of angle K. Well, I don't need angle K to find angle K right now, but what I do know is that that angle has been cut in half, which means those two angles are equal. If you will label the things you learn as you write, as you read through the problem, it'll help you to process through it. So we know that 3x minus 15 is equal to 5x minus 39. So now it's just an algebra problem. Subtract 3x from both sides and add 39 to both sides. So 2x is equal to 24. Divide both sides by 2, and I get that x is 12. I didn't ask for x, I asked for angle K. Well, angle K was 5 times x plus 8, so it'd be 5 times 12 plus 8. 60 plus 8 is 68. So angle K would be then 68 degrees. Okay, so there are a lot of vocabulary words and you've got to remember what they do, but angle bisectors have to originate out of an angle so they can cut it in half. Perpendicular bisectors cut segments in half. They don't care about angles. If they happen to pass through them, fine, but it doesn't have to. And an altitude goes from the vertex. Think of it, we got to have a place to hang the string. It's got to go from the vertex, and then it's going to meet the opposite side at a right angle. Okay, the angle bisectors intersect at the incenter. The perpendicular bisector intersects at the circumcenter, and the altitudes intersect at the orthocenter. One thing to keep in mind with altitude is because it's perpendicular, if you're on a grid, you might end up using your slopes, and remember perpendicular slopes